Welcome back to Applied Mathematics. In this video, I wanted to introduce you to sets of numbers. The idea of a set is one of the most generalized concepts we have in mathematics, and in a lot of ways that's what makes it so powerful. Sets can contain anything that you would like them to, and there's nothing specific about numbers that makes them special when dealing with sets. But this being math class, it's probably not going to be much of a surprise to you that most of the work that we do is dealing with numbers. So let me get my head out of the way and let's write down a little bit more formally what I mean. A set is a collection of objects, and we call those objects the elements of the set. And yes, the convention of sets is that general and that vague. The most common way that we talk about sets is by listing them out using what's known as roster notation. We start off with a curly brace, which in this context is called a set brace, and we just list out things. So for example, if I want a set that contains the number 42, the color red, and the pen that I am writing with, I can just list those out, comma separated, and then finish off with a closing curly brace. Again, collectively, we call those things the set braces when we're talking about a set. One important thing to keep in mind when dealing with sets is that there is no order to a set. So I could just as easily have written this as the set of red, pen, and 42. They are the same set. It does not matter what order we list the elements of the set in, as long as they are all there. I said I was going to be talking about sets of numbers. Let's go on to the first big set of numbers, which is known as the natural numbers. The symbol for the natural numbers looks like this. It's a letter N with an extra stroke in it. When you're typing this out, you can just use a bold letter N. The extra stroke is a nice way of typing something that's bold without having a bold character. You don't necessarily need to know the symbols for our purposes in this course, but depending on where you are going beyond this course, it might be something useful, and it's pretty easy to deal with, so I thought why not mention them. And the natural numbers are also known as the counting numbers. They are the first set of numbers that you ever learned when you learned how to count, starting at 1, 2, 3, 4, and so on. I'll just use dots, ellipses to say this keeps going because I would literally be here forever otherwise. An interesting debate in the world of mathematics is whether or not the number 0 belongs in the natural numbers. And it might be surprising to learn this, but that actually depends on the language you are speaking. The convention in the English-speaking world is that the natural numbers start counting at 1, And everyone is happy with that except for computer scientists. Computer scientists want to start counting at 0. And for reasons that I don't understand, the French also want to start counting at 0, as do a couple of other spoken languages. So we have a different set that we generally call the whole numbers in English. Every now and then you'll see it represented using the same symbol of n, but we're just going to use no symbol for it whatsoever, and we're going to tack in 0. Other than that, it is the same set. One of the interesting ideas of set theory is the idea of subsets, when every element in one set, like the natural numbers, is also an element in a second set, like the whole numbers. So let's go ahead and just call this W so I can write things down. And I can say that the natural numbers are a subset of the whole numbers. Every natural number is also a whole number, but there are some whole numbers, exactly one in this particular case, that are not natural numbers. And with the natural numbers or the whole numbers, we can do a lot of the work of arithmetic. Addition and subtraction work beautifully most of the time, addition all the time. Multiplication works all of the time, division every now and then. Right? It's a little bit easier to fix subtraction, so that's where we go next. Subtraction works most of the time. If you have 7 minus 3, you get 4, which is within the whole numbers, no issues whatsoever. If you try to subtract the other way, 3 minus 7, that doesn't work. So mathematicians had to invent a new type of number in order to perform this operation. We call that next type of number a signed number, or more specifically, the integers. Right? The integers are the signed whole numbers. The symbol for integer is a z, which makes absolutely no sense until you learn that this idea was first developed in Germany. And the German word for integer starts with a z. And because mathematics tries to be an international language, we've just kept it, and everyone uses the letter z to represent the integers. For the integers, I have to continue onward in both directions because we have the positive numbers going forever to the right. We have the negative numbers going forever to the left. Now that we have the integers, it's sometimes interesting to be able to talk about the absolute value of a number. The absolute value is denoted using vertical bars. So this notation is asking us to evaluate the absolute value of x. The technical definition of absolute value is the distance from x to 0 on a number line. And one of the nice things about the idea of a distance is that distances are always positive. Right? If you don't believe me, I invite you to build me a table that's -5 feet wide. If you're able to do that, I can probably get you a $1 million prize. I just ask for a 10% finder's fee. But distances are always positive, so absolute value is always positive. If I want to take the absolute value of a positive number, like 7, I get 7. If I want to take the absolute value of a negative number, like -7, I also get 7. This can get confusing sometimes when absolute value shows up within a longer expression. So one of the things that you see fairly frequently is the opposite of a number. If I put a negative in front of a set of parentheses, the opposite of 7 is -7. But if we combine these ideas together, we might write out the opposite of the absolute value of -7. Well, to evaluate this, we start by taking the absolute value of -7, which is 7, and then we take the opposite of that. We have to take 2 steps in this process. So the opposite of the absolute value of -7 is -7. Right? The absolute value is not the reason that this comes out negative. The absolute value is one step in a multi-step expression in this case. We'll be playing around a little bit more with absolute value and some of the things we can do with it a little bit later on. It should be something that you've seen previous to this course, at least in passing, but it may have been a while since you've thought about it. So I wanted to mention it now and get it fresh in your head for later. With that, I think we are done talking about the integers. We can now do all of the addition and subtraction we want to. Multiplication still works fine, but then we might try doing division, and division can give its own set of problems. That takes us to the next big set of numbers, which are known as the rational numbers. We'll use the letter Q to represent the rational numbers, which again doesn't make any sense at first glance. Until you think about them as the quotients. A quotient is the result of performing division, and the rational numbers exist so that we can perform division. The rational numbers are messy even by the standard of the other sets that we've talked about so far. In fact, we can't just start writing out a list of them the same way we have. So instead, we use a different tool for writing the set of rational numbers. It's known as set builder notation. We put our curly brace here still, and then I'm going to put a prototype, which in this case is P over Q. And then I put a vertical line and I describe what's going on with that P and Q. In this case, P is any integer and Q is any natural number. Right, so this is called set builder notation. And when you read set builder notation, the general format, general expression here is the set of all whatever your prototype is, in this case p over q, the vertical line is read as such that, and then you read whatever comes from there, which can vary wildly in its appearance. So the rational numbers q are the set of all p over q such that p is in Z and Q is in N. One of the problems with this definition is that it overdefines values. Just thinking about simple division, 6 divided by 2 is equal to 3. 15 divided by 5 is also equal to 3. So, just from that, 3, 6 over 2, and 15 over 5 are 3 equivalent fractions. They are 3 things that give us the exact same value. And so, whenever we're dealing with fractions, we always have this idea in the back of our minds of reducing fractions. And again, the vocabulary here will vary. I tend to say that we want to reduce to lowest terms. You'll also see things involving simplest form or simplify, right? Express your answer in simplest form, express your answer as simplified as possible, simplify your answer, write your answer in simplest form. All these things mean the same thing. The goal here is to avoid the ambiguity of several fractions that have the exact same value. And we do that by looking for common factors. So for example, if I have the fraction 24 over 32. Now 24 and 32 have a common factor. If you can find the greatest common factor, which in this case is 8, you can get this done in one go. If you don't see that right away, you might see something a little bit easier. 24 and 32 are both even. So maybe you divide top and bottom by 2. That takes us to 12 over 16. 12 and 16 are still both even, so we divide by 2 again. That takes us to 6 over 8. And once again, both even. So once again, divide by 2. And that takes us to 3 over 4. And 3 over 4 is the simplest form. That's the lowest terms for this fraction. I am not going to be picky about how you write out reducing to lowest terms. Once again, this is not a skill that I expect is new to you. It may have been a while since you've seen this before, but it should be something that you have seen, you have practiced, you have worked with. I just want to remind you that it's something that needs to be done. A little bit later on, we're going to talk more in depth about fractions, and I'll show you some shortcuts on a calculator that will let you work with fractions more quickly, one of which will allow you to reduce the fraction if your calculator is capable of that. So I'm not worried about can you perform this process of reducing to lowest terms right now. I am concerned about, do you understand that it's something that needs to be done? And can you recognize that two fractions are equal? Can you recognize that a fraction has not yet been reduced to lowest terms. Right? That last one can be tricky. I showed you in this example, the easiest thing to spot is, are the fractions both even? If they are, divide by 2. If the numerator and denominator of the fraction both end in a 0 or a 5, you can divide by 5. And then another one that's a little bit trickier. Add up the digits in the numerator, add up the digits in the denominator. Keep going until you get a single digit number. If that result is a 3, a 6, or a 9, divide by 3. Clear out a little bit of space here so I can show you one last example how that works. If I have something like 111 over 135, 1 plus 1 plus 1 is 3. 1 plus 3 is 4, 4 plus 5 is 9. So I know that 111 and 135 should both be divisible by 3. Again, for the most part in this course, I'm not going to worry if you just use a calculator to perform the division, but for right now, let's get a little bit of practice with long division. It never hurts to know how to do things by hand. 3 goes into 111. Well, 3 doesn't fit into 1, 3 fits into 11 3 times. 3 times 3 is 9, subtract that off. 11 minus 9 is 2, drop down the next digit, which is 1. 3 fits into 21 7 times. 7 times 3 is 21. Subtract that off and you get 0. 3 goes into 135. 3 fits into 13 4 times. 4 times 3 is 12. Subtract that off, you get 1. Drop down the next digit, which is 5. 3 goes into 15 5 times. 5 times 3 is 15. Subtract that off, you get 0. And so we see that 111 divided by 3 is 37. 135 divided by 3 is 45. And you can check from here, right? Those ideas that we just talked about. Make sure it's not divisible by 2, by 3, or by 5. And that takes care of just about every possibility. You can keep going from there and work your way through the prime numbers if you would like. After 5, you check 7, and 11, and 13, and 17 and 19. I don't have any cute tricks for checking any of those values. Unfortunately, it's just a matter of brute force. But I invite you to try that on these. Recognize that they don't work. And so we know there's nothing else we can do. Moving onward. The next set of numbers that I want to talk about is the irrational numbers, which we define very vaguely as numbers which cannot be written as a fraction. The most commonly used example of an irrational number is pi, the circle constant. Right? You've probably been forced to memorize at some point in the past that pi is about 3.14. You might have even been forced to memorize the fraction approximation. Pi is approximately 22 over 7, but that's again an approximation, not actually the value of pi. If you had a math teacher as cruel as my calculus teacher, you were forced to memorize that pi is 3.14159. And if you had a roommate like I did who participated in pi recitation contests, then you heard pi recited enough that you can give a few more digits. Not that it's of all that use to get that much further than this, because if I need to use the value of pi, I grab out my calculator, I push the handy dandy pi button, which just puts the value in for me and I don't have to memorize anything. Right? Pi is famously a non-terminating, non-repeating decimal value. These digits continue onward indefinitely, and they seem to proceed mostly randomly. One of the interesting questions that mathematicians are trying to figure out how to answer, not as much because the answer itself is interesting, but because we don't know how, and inventing a tool that will allow us to do this seems like something that might be useful for something else somewhere along the way. But we don't know. Are the digits of pi actually pseudo-random? That is to say, is it equally likely that any given digit will appear if you continue to trace out the expansion of the decimals of pi? All that will be on the course. The important thing is that because it is a non-repeating, non-terminating decimal, that means that we don't have a way of writing it as a fraction. Another classic example of an irrational number is the square root of 2. Later on in this course, we will talk about the Pythagorean theorem, which can be used to verify or to prove that the square root of 2 is not a rational number. And for the reasons that it shows up there, it's also useful when dealing with triangles to know the first couple of digits of the square root of 2, 1.414, etc. But once again, I don't need to know that. I just punch the square root of 2 into my calculator and it tells me the rest from there. I unfortunately cannot give you a nice, concise, set-based definition of the irrational numbers. Excuse me. I unfortunately cannot give you a nice, concise, set notation definition of the irrational numbers because there's actually a lot going on here. There's a lot of different kinds of irrational numbers, these two being two of the four poster children that I know. Pi is the first of a set of numbers called the geometric numbers. The square root of 2 is the simplest of a set of numbers called the algebraic numbers. There are also a couple of other sorts of numbers that just do not behave well and give us all sorts of craziness. How and why, beyond the scope of this course, just knowing that they exist is good enough. The irrational numbers on their own, though, are not all that useful. They do give us a completion. The last set that I care about is the real numbers. The set of real numbers is given using a Blackboard bold R. And the real numbers are the union, the combination of the irrational numbers and the rational numbers. The real numbers are the set of numbers that we deal with in algebra. The real numbers give us most of the tools we need for work in algebraic structures. There is one more further extension that is useful in some applications called the complex numbers. We're not going to get to any of those applications in this course, but anyone who continues to the second part of this sequence will get to see all of those at that level. With that, we have our sets of numbers, and being able to classify numbers between those sets is useful in its own right. There are a couple of other classifications we can use for numbers. A common one is a constant versus a variable. A constant is a known fixed value. A variable is an unknown that can be used in a couple of different ways. Sometimes it's used as a placeholder. For example, if you want to calculate the circumference of a circle, you take pi and you multiply by r squared, where r is the radius of the circle. I don't know the value of r because I haven't seen the circle that you are looking at. But if you have a circle, you can measure its radius, you can then plug it into the expression, and the value you get out will be the circumference of the circle, the distance around the outside. So variables are very nice in placeholders in that regard. I mentioned earlier in this lesson, even when we were talking about the absolute value of x, I used x as a placeholder there. Variables are also very valuable in situations where you deal with indirect measurements. Right. This is where algebraic equations come in, places where you will have instructions of solve for x. We're going to talk about both of those situations in quite a bit more detail a little bit later on in the course. Again, for right now, I'm just trying to give you the vocabulary, ways of talking about numbers, make sure that everyone is coming into this course on the same page. There is one last way that I can classify numbers, and that is as literal or denominate. A literal value is represented as a symbol. And a literal value is generally expected to be exact. For example, pi, that we've been talking about quite a bit in the last few minutes. When I write down pi, that is exactly the ratio between the radius and the circumference of a circle, or well, the diameter and circumference. Sorry, I misspoke there. Practically speaking, whenever I need pi, I'm going to write down that approximation of 3.14 or whatever it is I happen to be using, which takes me away from the exact value. It's no longer literally pi, it's an approximation of pi. You can also do this for physical constants, right? The letter c in physics is often used to represent the speed of light. We don't actually know what the speed of light is exactly, or at least we don't as of the time I'm recording this. The particular definitions of units of measure gets a little bit fuzzy and we change them every now and then. So that might not always be true, but we don't need to know the exact value of the speed of light. We can just write down the letter c. In practical application, I know that the speed of light is about 3 times 10 to the 8 meters per second. And if I need to use it in a calculation, I can write that down. Or 670 million miles per hour. It's not exactly the speed of light, but it's close enough and it will let me do the calculation. But it's not literally the speed of light, so it's no longer a literal once I've done that. The other place that literals come up is in variables. Every variable is a literal value. Contrast that with a denominant value, which represents a measurement. So for example, I might measure the height of the wall behind me, which comes out at 7.23 feet. I know decimal feet, kind of weird, but I was able to do it, so I did it. Or using compound units, my own height is 6 foot 2 inches. Those both represent measurements. I counted the number of ports that are available on the computer where I'm recording this video. There are 27 of them. Units aren't explicitly given in that, but it is a measurement. I've actually seen some debates as to how esoteric things can get with a denominant value. There are some people who insist that a denominant value must explicitly include the units of measure. There are some people who insist that anything that's not a literal is a denominate. I'm not going to get in the middle of it. I don't care that much. I just wanted to mention that this is a thing that we can talk about. So for example, the speed of light, c, is a literal. If I write it out as 3 times 10 to the 8 meters per second, that's a denominant value. Pi is a literal. If I write it out as the decimal approximation 3.14, I'm not sure if it's a denominant value or not. Again, depending on who you ask, you will get different answers. I don't want to get into the middle of it. That's not important for this course. I'm not going to use the terminology of denominant value much at all in this course, but literals do come up in the strangest of places, so I wanted to make sure that you knew what I was talking about as I got there. All right. A lot of vocabulary in this video. I know the first lesson in any math class tends to be a ton of vocabulary. No one likes it, including the instructor. Luckily, from here, we are going to move on to do some things that are a little bit more interesting. But for right now, I think that's enough, so I'll wrap up here. Thanks as always for joining me. I'll see you next time.